Welcome back. So we will continue our discussion on some of the important practical considerations while acquiring the NMR spectrum and how do we process that? How do we acquire the data and how do we process it? We are discussing varieties of points about acquiring the time domain signal. How do we acquire the signal? Of course, we'll discuss about the processing later. So now we'll continue further. Last week we discussed about signal to noise ratio and varieties of things. Now today I will discuss about something more like pulse phase and signal phase. Remember, we discussed this at some stage earlier. This is very important while acquiring the signal. Now let us say I am going to apply a pulse along some axis and bring the magnetization, which is initially under thermal equilibrium, along z-axis to x-axis. Now, my detector, let us say, is along x-axis. I'm seeing as soon as you bring the magnetization, immediately after the pulse, you bring the magnetization to x-axis, they are all in coherence. Okay, and all these spin vectors are in coherence. So we will detect maximum signal here. That's what I said for T2 while discussing. Then afterwards they will start, there is a decoherence afterwards. So this is a coherence. Statistically, you will say there is a coherence of all the nuclear space spins along this axis. All the magnetic moments come there. Now if I do the Fourier transformation, remember I am going to get real part and imaginary part. The Fourier transformation contains real part and imaginary part. Real part is a cosine part. You see, it starts with, it is a cosine function, decaying and oscillatory. If you look at this one, and when you do the Fourier transformation, I get a signal which is in phase like this. This is called absorptive signal. On the other hand, because MS can be resolved into two components, this I call the signal SX, let us say, XX component or SY component. This is signal here. SX is a cosine component. It is called real part of the spectrum or absorptive peak. And SY is the imaginary part of the signal. If you do after the Fourier transformation, you will get a dispersive signal like this. Real part is always absorptive and imaginary part is dispersive. Okay. And now the signal is along x-axis. My detector is also along this axis. Now I am going to see this type of signal in the frequency domain. Real part is like this, imaginary part is dispersive. Let us say I will bring the magnetization instead of x-axis somewhere in between x and y axis. Okay, let us say from z axis I'll bring it somewhere here, which makes an angle phi with respect to x axis. This is my detector. Now the magnetization mx is not maximum like what you expected when all the signals instantaneously, all these my spin packets or my vectors are brought to this axis, creating phase coherence. Here we have brought it at 45 degrees. Let us say some angle phi. Now you have to resolve them into two components. You have two components here. Cosine and sine component both are present here. Now it is not a pure phase. Unlike here, where you are getting real absorptive and dispersive signal in the imaginary part. Now there is a mixed phase here. So because of this mixture of absorption, phase is not exactly like along x-axis. All these pins are not along x-axis. Now there is a mixture of absorption dispersion modes. We get a mixed phases. Look at it. This is the type of signal you are going to collect. Instead of then after Fourier transformation, the real part is not exactly absorptive. There is some phase. This thing is the phase mixture of imaginary and real part. Both are present. So as a consequence, there is a phase shift. Same way in the imaginary part also. You see the dispersive part also, dispersive signal is also not exactly like what you should have expected. Okay. Remember, this is I am applying a pulse along some axis minus y, brought the magnetization here. You can apply any angle of the pulse. The magnetization which brings to x-axis or y-axis from z-axis is called 90-degree pulse. I can continue further for like this is 180, go back like go continue like this, it is 270, and go like this is 360. I can keep on making the magnetization to rotate along this axis, along this plane continuously it can rotate. On the other hand, I can bring it to any axis, then I can have mixed phases like this. Fine. Now I'm looking at this one. Some pulse I'm applying, I have just written apply X pulse. You can find out was it right or wrong. I told you how we shift the magnetization is flipped to a particular axis by you can apply right hand thumb rule and find out which direction it is flipping. If I apply magnetization along X axis, magnetization is along Z axis. Let us say this is considered to be X axis and this is Y axis. Okay. Now the magnetization has come to Y axis. So which direction you have to apply the pulse? Because y-axis is this side, x is along this axis, magnetization along this axis. Imagine a three-dimensional axis. Now my detector is here and magnetization along y-axis. So what did I do? Apply a x pulse, magnetization along z-axis, curly fingers you see, it came to y-axis. So now my detector is here. What is the type of signal I am going to see for real and imaginary? Remember, now the real part which was here has gone here. That means real part appears like absorptive and imaginary part appears like absorptive. Interesting, right? So just because of 90-degree phase shift, you shifted the magnetization from x-axis to y-axis, but your detector is here. Now, when you do the Fourier transformation, look at the frequency spectrum, you will find now the real and imaginary part have interchanged. They are out of phase by 90 degree. The real part is now dispersive, and imaginary is absorptive. Okay. On the other hand, I'll do one thing. I'll apply a pulse along y-axis, no problem. You can find out whether it's right or wrong by application of right and thumb rule, and bring the magnetization to, let us say, minus x-axis. What is going to happen? My detector is here. Now it is seeing the signal in this direction, opposite. It is actually the real part is a negative absorption. Okay, real part is negative absorption, and similarly, imaginary part compared to this one is reversed. In the previous example, you would have seen, I think. So this is real part is a negative absorption. That is important point you see because you are seeing here. On the other hand, if it had come here, that would have been a different thing. You can work out. So this is the way by the application of the particular pulse of particular angle in a particular direction, you can find out the phase of the signal. Okay, after Fourier transformation, how does the signal behave? Whether it is real is absorptive component or imaginary, is it dispersive or vice versa, or there is a mixed phase. This is how you can play with the pulses, play with the direction in which you are going to apply the pulse, and manipulate the direction in which you can flip the magnetization. That is a very, very important concept. Remember, this is what people do when we design the pulse sequences. Okay. Now, next another point I wanted to tell you is we need to set the carrier offset. Okay. Remember we discussed about the rotating frame, etc. I need to bring the carrier exactly on resonance. Then frequencies on the right side is faster component, positive frequency on the right side of this carrier. On the left side of the carrier frequency, these frequencies are negative. So these are all positive and negative frequencies, I will say. But I have to, I need to have a receiver. The receiver, if I keep it one place, let us say, I will show here. I have to choose the carrier offset in such a way. First thing, I have to get uniform excitation. You know, we are applying a square pulse or a rectangular pulse, you can consider depending upon the width. If you take the power spectrum of that, okay, do the Fourier transformation of that, This is the type of spectrum you are going to get. This is called sinc function. And you see, if T is my pulse width, there is a zero crossing of the sinc function at minus 1 by T and plus 1 by T. Okay? And now, let us say I have to cover a 5000 hertz spectral width at 500 megahertz. Where do I take the spectral width? My spectral width will be defined from the carrier frequency, that 5000 hertz. Let us say this is my carrier frequency. I sit here or I sit here and cover 5000 hertz. That is not good for me because it is not a uniform excitation here. And some places they hear, there won't be excitation at all. We have to ensure all the frequencies, all the spins which are within that chemical inequivalent spins which give frequencies in 0 to 10 ppm, all this should be equally excited, uniformly excited. In which case, you have to choose the spectral width and carrier offset in such a way you focus on this region. Okay? When you focus on this region, then this is quite a bit. You can file, in fact, we calculated earlier for a 10 microsecond or 5 microsecond pulse width of proton. If I take, this is about 100,000 hertz, this is about 100,000 hertz, 200,000 hertz, 200 kilohertz will be there. And in this region, this is very small. All I require is only 5,000 hertz. Very easy. And this 5,000 hertz at the center is of uniform power. See, the power is uniform, almost uniform. Is like, I can say horizontal, unlike here and here, which is zero crossing. Here, for example, power is much less. Here is much less. So I choose this region and make the spectral width in this region so that all these spins are uniformly excited. And for that, I need a carrier frequency. 5000 hertz from where? I have to set a carrier offset. I can put at one end of the spectrum here or here, wherever I want. Let us say this is my spectral width. I can put my carrier offset here. Or I can here on one end of the spectrum, right or left. Does not matter. And then from that place, from that carrier frequency, I can cover this 5000 hertz spectral width. This is called carrier offset, which we have to do. If the carrier offset is far away, for example at zero crossing or something, you will not have uniform excitation. That is very important to remember. So if I have to do that, I use a single detector. See, we have both real and imaginary component after Fourier transformation of a time domain signal. It can detect either of them. We have a single detector because real and imaginary, I saw the phase of the signal. Just now I showed you. Sometimes they will be out of phase by 90 degrees. They are exactly out of phase 90 degree. Real and imaginary. One is absorptive, other is dispersive. A single detector, if I have, it can either detect real signal or imaginary signal. It cannot detect both. In which case, let us say, if my carrier is somewhere here, I cannot distinguish whether it is a signal, positive sign signal or negative, positive frequency or negative frequency. I cannot differentiate at all. All doesn't matter. I skip at one end. Then also I can see on one end, either I can get only one sign, either it could be positive or negative. I cannot distinguish. So in any case, to avoid confusion, always in the single channel, when there is only one detector, the carrier is put at one end of the spectrum. Okay, somewhere here or here we put and collect the signal. But only the disadvantage is you cannot distinguish between positive and negative frequencies. But better to detect both real and imaginary. There are lots of advantages in deciding how the magnetization behaves, to decide your pulse sequence, everything. You need to detect both real and imaginary advantages. Also, there are various reasons why. First thing, you can distinguish between positive and negative sign, negative signal. That's one thing. At the same time, there is a lot of gain in the signal to noise ratio also. For example, if I go here, although I'm putting my receiver here, remember my Nyquist frequency? There are certain frequencies here on this side. It may be noise. Noise has higher frequency than this. This is my region of interest. This noise will fold back here. Entire noise will fold back into the spectrum. Is it not? Noise beyond this carrier offset has to fold back into the spectrum. So the noise level will be there. On the other hand, if I have two receivers, let us say, one to detect real component, one to detect imaginary component, one to detect cosine signal, one to detect sine signal, which are out of phase by 90 degree. If I have two receivers which are out of phase by 90 degree, then it is better. I can distinguish between cosine part and sine part, in which case I can distinguish positive component, negative component, positive peaks with positive sign and negative sign. I can distinguish. Well, how can I do that? What I will do is, I will, if I have to distinguish this thing, I am going to put my carrier at the center of the spectrum. Not here, written here. Okay, if I have a carrier spectral width here, I'll put my carrier here. And positive negative signal I can understand by having two receivers. I'll detect MS component in one receiver and MY component, that is MX component is a cosine part, MY part is a sine, MY signal is a sine part. I can detect them individually in two receivers. But in reality, there are no two receivers. It is only a manipulation of the Euler function equation. You know that e to the power of minus I theta, which is a cosine function plus I sin theta, I cos theta plus I sin theta. So we do mathematical manipulation in such a way by adding and subtracting signal, we can detect only one component. That is possible. This is called a quadrature detection. And before that, I want to show you how the signal detection sine and cosine part works. For example, if I detect mx component cosine signal, this is a cosine signal, I do the Fourier transformation, I get minus omega and plus omega, two frequencies. Both negative and positive frequencies are there because cosine is a even function. It cannot distinguish between positive and negative frequency. Cos phi equal to cos minus of phi. That you know trigonometry. If I detect the my component, sine signal, and do the Fourier transformation, one is positive component is this one, negative is out of phase by 90 degree. It's the inverted signal I get. Now what I will do is, I will do co-add these things. I'll take the Fourier transformation of cosine function and sine function. I do the co-addition. I get this one. I know if my carrier is here, I know what is the signal here. And if I subtract, let us say, I can get only this part, this component. Then I know what is the frequency here. So I can manipulate the cosine and sine functions in such a way I can add and subtract and detect either cosine component, sine component. This is what it is. In the quadrature detection, the carrier frequency is set at the center of the spectrum. Now these are all signals with positive sign. These are all with negative frequency. These are positive frequencies and these are negative frequencies. So that's why quadrature detection is what we are going to routinely utilize. Because of course there are some lot of difficulties if they both sine and cosine compare two receivers if they are not exactly out of phase by 90 degree. What happens? If it is, let's say, they differ by 5 degrees, not exactly 90, 85 degree difference is there. Because cosine and sine function should be exactly out of phase by 90 degree. If the phase angle is differing, we have a mixed phase. But in such type of quadrature detection, what happens is you are going to get some additional peaks, some extra leakage. That is called quadrature images. And of course, in the electronics, we need to have a gain for the receiver, one receiver and the cosine and one receiver for the sine. We should have equal gains. In the electronics, it should be such that both the receivers should have equal gain. If the gain is not equal, let us say cosine component has a better gain than sine component by some degree. Little bit of difference is there. That can also cause what are called quadrature images, which cannot be corrected. They have a different phase altogether. So these are the things which we should know, but I'm not going into the details of the quadrature detection. And there are lots of problems in that and lots of advantages are there. If you are not very good, it gives problem. If a perfect quadrature is there, it's very advantageous. And we use that in very large number of experiments. But anyway, without going more into the details, I told you What is the advantage of quadrilateral detection? What is the advantage of single channel detection? Now, let us discuss more about the radio frequency pulse. Now, up to this, you have done something, but you need to now start collecting the signal. How do you start collecting the signal? You have to excite the nuclear spins by application of radio frequency pulse in a direction perpendicular to the magnetic field. That is that direction. Magnetization is here. I have to apply in a direction perpendicular to it and flip the magnetization to transverse plane. Now the question is, what type of RF pulse you are using? What is the width of it? What is the power of it? This is another thing we should know. Another interesting thing is the frequency generated is a single frequency. RF, we are having a single frequency. It's a monochromatic radiation. What is the transmitter which generates frequency is only one frequency. But what is happening in our spectrum? We have so many frequencies, so many peaks are there in the 0 to 10 ppm range. There may be 50 peaks. How do we exit them? Because this frequency has to match the energy separation to get into a resonance condition. But we are having a monochromatic radiation, so it should match only one of the frequency or between one of the two energy levels. How is that? How does it work? And remember, NMR spectrum is a wide range of frequencies covering large spectral width. So in the first instant, you will guess you cannot exit all the frequencies in a monochromatic radiation with a single frequency radio frequency pulse. But it is not true. What is happening is we have a multi-frequency excitation. The reason is we have to take into account Heisenberg uncertainty principle, which tells us that an excitation pulse of duration delta t has associated with it uncertainty of frequency spread like this, 1 over delta t. You understand? I have a pulse duration. It is, let's say, 5 microsecond of a single frequency, no problem. And then there is a spread in the frequency, 1 over 5 microsecond. Imagine, we will cover a wide range. You can cover 200 kilohertz. This is the reason. Although you apply monochromatic single frequency RF, but the excitation is all the peaks of the entire spectral width range. This you can understand more by uncertainty principle. There are lots of books which can explain these things. You go to the electrical engineering book about radio frequency, it will tell you everything. All those things you can understand. Even a couple of very good NMR books will discuss this. Effectively, the RF pulse behaves as if it is a polychromatic pulse, pulse of multi-frequencies. And now what I said delta t is called duration of the pulse. Very important, know that. Delta t is referred to as the duration of the pulse. The pulse width can be manipulated by the duration and the RF power together, power of the pulse. You can combine these to iterate in such a way you can manipulate the magnetization the way you want to flip. It can flip by 90 degree, 180 degree, 45 degree by manipulating this RF pulse width and the RF power. Okay, now you know that. So supposing I want to have a pulse width of 10 microsecond. What is my frequency spread according to uncertainty principle? It is 1 over t, 100 kilohertz. So the amplitude of the power spectrum goes from 1 over t to minus 1 by t. When the RF power is 0, I saw in the sync function I showed you, at the 0 crossing, there is no excitation possible. So your spread of the frequency should be such that it should be, as I told you, it should be uniform at the center of the power spectrum. So if a spectral width is, let's say, 10,000, it should be plus or 5,000 plus or minus 5,000 from the center of this power spectrum. Then you will get uniform excitation. And now the question is, how do I deal with the power and the pulse to get the 90 degree pulse or 180 degree pulse of my liking, of my choosing? Whatever I want, I should choose. Remember, mathematically, you can calculate like this. The angle of the pulse, angle at which you can tilt the magnetization from z axis to any of the other axis, is governed by an equation called gamma star Tp star B1. This is an RF power. Gamma is the gyromagnetic ratio. Tp is the pulse width. You understand? If you have to tilt by 90 degree, you have to know this angle is known, gamma is known. You have to play with these two, pulse width and the power. That's what I said. You can play with the pulse width and the power so that you can decide, you can design the pulse of 90 degree, 45 degree, 180 degree, whatever it is. So remember, important thing, how do you calculate the pulse? Which angle of the pulse? The flip angle of the pulse is given by gamma Tp into B1. This equation is very important to calculate the flip angle. Now experimentally how it is done? The variation of the intensity of the peak as a function of flip angle is monitored. How it is monitored? Look at this. I have to collect the signal. I take some standard sample. Let us say one which gives me a single peak. I do not know what is my 180 pulse. I do not know what is my 90 pulse. But I have to calibrate. What I will do is, I'll put the sample in the magnetic field. I'll put the sample in the magnetic field. Set the pulse width, let us say 2 microsecond or 1 microsecond. Start with a small value. Collect the signal. Do the Fourier transformation. Get the frequency spectrum. Measure the intensity. Now, where is the pulse width? 2 microsecond, 3 microsecond, 4. Of course, all in microseconds. Pulse width cannot be very long. And of course, this pulse width of few microsecond, you can convert it to frequency. How much is the power of the pulse in the expression frequency? It is of the order of 25 to 30 kilohertz normally for the excitation pulse. Okay. So, keep on varying the pulse width without changing any other conditions. Power remains same. Vary the pulse width. Then you keep on measuring the intensity. See, the intensity follows a cosine curve or sine curve like this and reaches maximum here and then keeps decreasing. It becomes zero, goes back, goes back, goes back like this. So what is happening? I remember I told you the magnetization can be brought by to flip by, can be flipped to any axis by any degree. Along z axis, it was there. This is a thermal equilibrium. This is a bulk magnetization. I apply 2 degree, comes here 5 degree, 10 degree, 20 degree, and I want to bring it to x axis. I am applying in some particular direction perpendicular to z axis. I brought it to 90. I can take it slowly, increase the width. Now angle become 95, 100, 120, 180. Keeps increasing 200, 250, 270. Then come back to, so you can make the spins to oscillate. The magnetization keeps on rotating in a particular plane. So, if I have a detector somewhere here, I say, let us say I am bring the magnetization to x-axis. My detector is along x-axis. That's what I discussed about the phase of the pulse. Then I get maximum signal. Now I do not change my receiver place. I receiver is the same axis. Keep on, when it go to 180 degree, when the signal is from z axis come to minus z axis, if my receiver is here, you will not get any signal. It is zero. And at 270 degree, you get negative signal. Again 360 is zero. So it keeps oscillating. So you find out what is the maximum intensity, where you get, that is a 90 degree pulse. If you have a difficulty, you can look at here, for example, all are more or less of equal intensity. And you do not know which one to select as your 90 degree pulse. That difficulty will be there. What I suggest is, look for 180 degree pulse. Signal has to be zero. You know what is 180 degree pulse? You measure in microseconds. Take 50% of that. Half of that. That is 90 degree pulse. If 180 pulse is, let us say, is 10 microsecond, take half of that and it is the 5 microsecond. Now do the another experiment, setting angle to be 5 microsecond, you get maximum signal. That is your 90 pulse. That is the way you have to calibrate the pulse, 90 degree pulse. Not only 90, any angle. I give an example, how to calibrate the 90-degree pulse. What you have to do is to vary the duration of the pulse as a function of duration of the pulse, collect the signal, measure the intensity, make it to go through one complete oscillation, find out at what is the signal. It will be zero at a particular place. That signal, that angle correspond to 180-degree. Take half of that is 90. Then rest of the things is simple manipulation. Okay. This is the thing which I wanted to tell you as far as the data acquisition is concerned. We discussed lot of points, lot of things we discussed in right from the sample preparation to data acquisition. Okay. Now you have done an experiment with various ways by calibrating pulse width, setting spectral width, and then carrier offset, quadrature, single channel, everything you knew. Shimmed the magnet, got better resolution, you understood what is the line shape, everything you have done. But now you have to process the time domain signal. Of course, here itself you already done by calibration. You already processed the signal. Doesn't matter. I'll tell you more of the process. This is just to, because I had to tell you 90-degree pulse. I said you already Fourier transform and you already done that processing done. But much more can be done. We'll discuss how do you process the time domain signal in the next class.